Dear students, today we are going to discuss the use of potentiometer to find the internal resistance of a primary cell. Here we are using the same principle of finding the EMF of a cell by using potentiometer, which we have already discussed earlier. And apart from this, we will also find the expression for internal resistance of a primary cell, and we will feed the value or the ratio of EMF of the cell and the potential difference across the cell when some load is attached, R1 load is attached to the cell, so that once we find this ratio E by V1, we will be able to replace its equivalent value obtained and determined experimentally, and putting that in the expression where you see it is given by the relation equation number 2, and then once we feed the value of E1 by R1, E1 by V1, we will get the value of internal resistance of this cell. So let us see how it is being done. First of all, let us look at the experimental arrangement. You see you have a potentiometer, 10 arms 1 meter long each, and we are again attaching a battery of high voltage. When it is connected to load, we assume that the potential difference across the battery is V, and this value of potential difference across the battery when it is connected to the load is always kept greater than the EMF value of the cell which is being used. If we don't do so, what will happen? We will not get any null point for null deflection in the galvanometer. We will not get any null point, so that our experiment will be defeated. So now you see we assume that the EMF of the cell is E1, and here if you look at this circuit, we are also attaching another circuit, a cell whose internal resistance is to be determined. We attach it to the galvanometer, and parallel to this cell we also attach a resistance box whose resistance R1 is plucked out, means the resistance R1 is introduced in the circuit by using this resistance box. So the value of R1 is known to us, and key K1 is used to draw the current from the cell when K1 is on, and not to draw any current from the cell when K1 is off. So this is the experimental arrangement, different from the previous one when we were only finding the EMF of a cell. So now look, you see if you keep the key K on and keep the key K1 off, it means that no current will be drawn from the cell E1 when galvanometer is showing null deflection. Say it is happening at point C where the jockey is being connected, and for that case we have EMF is equal to V upon AB into LAC. V is the potential difference across the battery, and AB is the total length of the potentiometer wire. So that is potential drop per unit length for the potentiometer wire, and that multiplied by the length at which the null deflection is found in the galvanometer, that means the length of AC. So we write length AC. So this is our equation 3, but before we apply it, feed it, we need to find the internal resistance of the cell. What is internal resistance? You see, total EMF is always equal to potential difference across the plates of the cell plus current into internal resistance, current drawn from the cell into internal resistance of the cell. You see, it is based on the principle of conservation of energy. Total EMF must be either showing up potential difference or potential drop due to current flowing through the resistance. So here you have E1 is equal to potential difference across the terminal of the cell plus potential drop across the internal resistance of the cell. So once we understood this, where R1 is the internal resistance of the cell and I1 is the current drawn from the cell by the load R1. Now you can very much understand that using the relation V is equal to I or the Ohm's law, you have V1 is equal to I1 R1, where I1 is the current drawn from the cell and R1 is the resistance used as a load for cell E1. So in that case, now if we divide both sides by V1, you get E1 by V1 is equal to V1 by V1 plus I1 R1 by I1 R2. Here you see I1 cancel each other, and so we are left with E1 by V1 is equal to 1 plus R1 by R1. Arranging this expression, we have internal resistance R1 equal to E1 by V1 minus 1 within the bracket multiplied by the load R1 attached to the EMF, attached to the cell E1. Let us call it equation number 2. Now if we have already understood that when no current is drawn by the galvanometer for K1 keeping off, it means that EMF of the cell E1 is equal to V upon AB into LAC. We have already discussed. This is our equation number 3. Now we happen to keep key K on and as well as key K1 on. Means both the keys are now kept on. Earlier only key K was on. So now K is on, K1 is on. That means some current is being drawn from the cell E1 by the load R1 attached in parallel to it. And for that case, the potential difference across the cell E1 becomes V1. And for this situation, if the null deflection is obtained at point D, then we can very well write that potential difference across the cell when some I1 current is drawn by load R1 will be equal to V1 equal to V by AB into LAD. You see, LAD means length of the wire AD multiplied by potential difference per unit length, that is V by AB. So we have V1 is equal to V by AB into LAD. We have E1 is equal to V by AB into LAC. On dividing equation number 3 by equation number 4, we get the ratio E1 by V1. V by AB is common in both, so they cancel each other. We have E1 by V1 is equal to LAC by LAD. Now when we put this value of E1 by V1 in this expression, we get L1 by AC divided by L1 by AD minus 1 into R1, giving the value of internal resistance of the cell E1. And so once we determine the value length AD, length AC, and we already note the value of R1 in the resistance box, putting their value over there, we can find the internal resistance of the cell E1. And in same manner, when you replace this cell by another cell, you can find the internal resistance of any other cell. Thank you and have a nice day.